Let me start the recording now. Okay. Okay. So, any ideas about which of these are correct?
So since P is equal to NP, so all languages which are there in P are there in NP as well.
Correct. Yeah.
And all languages in NP are there in P as well. That's fine.
Hmm.
All languages in NP are there in P as well. Yes, because the P has been proved to is equal to NP.
Hmm.
Now the thing is about the remaining two. So for all A's and A is NP complete. So that would mean what? That the problem itself is element of NP, and which is fine because P is equal to NP. Then all those problems which are there in P or which are there in NP can be reduced into this problem. So that will not be troublesome because
Mm-hmm.
one problem which is there in P can be reduced into the other problem which is in P easily. Because when the one problem says yes, I mean, I can always modify the output in such a way so that the other problem also says yes, and then it's fine. But now, so this seems true. But then, what is this that A is equal to phi and A is equal to cleaning closure of sigma? So, like, if I consider these two problems and which are there in P, and if I consider them, so why to exclude? So this option compels me to think that should I exclude these two extreme cases of the P languages in the NP complete? So what if this A is equal to phi? Then all the problems which are there in NP can they be reduced into phi? So, but then phi is probably the answer would always be either yes or no kind of the thing. That will not be
Exactly.
yes or no.
Exactly. Yeah.
So therefore, I would like to exclude this phi and the clearing closure of sigma,
Hmm.
and then A, B, and D. Three options are correct.
Yeah. Correct. So, yeah. Okay. So, as you said, if P becomes equal to NP, then clearly P is contained in NP and NP is contained in P. That's what we mean by P is equal to NP. So if P is contained in NP, then all languages in P are in NP. So therefore A is true, and also all languages in NP are in P. Therefore B is also true. So these, okay, what happened? Okay, so these two are correct. And yeah, as you are saying, if A is in NP, sorry, if A is in P, then um, yeah, then can we say that sorry, for all A in P, we can reduce A to, sorry, um, for all B in P, I can, okay, let the pencil charge for a second, sorry. Okay, so okay, if A is in P, then can we say that is A um, NP complete? We know that clearly A is in NP, that's for sure. But is it NP hard as well? That is it true that for all B in NP, you have that B reduces to A? This is the question. Okay, so okay, so since B is also a language in P, um, it should be true that B reduces to A. But the only catch here is that you want, when we say that this is a reduction, you want that X is in B if and only if sigma of X is in A. That is, if X is in B, you want that sigma of X is in A, is in A, and um, and You want that if x is not in B, then sigma of x should not be in A. Okay, but look at what happens if A is an empty language. Okay, if A is an empty language, then this second condition holds true. For every x that is not in the set B, sigma of x will not be in A, because A is an empty set, so in particular sigma of x cannot be in A. So condition 2 will hold true, but 2 holds true. But what happens to the condition 1? If x is in the language B, then you want it to map it to some sigma x which is in A. But that cannot happen. This cannot happen because A is empty. So for all x, sigma of x is not in A. So there is nothing that you can map the no instances to. So therefore, if A is V or A is sigma star, then there's a problem. In sigma star, 1 holds, but 2 is an issue. But 2 does not hold. So, excluding this phi and sigma star, which are like two corner cases, every other language A in P is NP complete. So, therefore, D is correct. Yeah, exactly like you said. So, any questions about this?
What about the reduction of? Can you slightly move down in the slide? Yeah. So what about this reduction from B to A? What kind of the reduction is this? I mean, should this function f runs in the polynomial time, or because both the problems are now there in P, so we would be requiring a transformation function which runs in lesser time. So what the time be? Like while transforming an instance of an NP problem into an instance of the another NP problem, this transformation was carried out in the polynomial time,
Hmm.
and we used to write P as a subscript here.
Hmm.
Now in this reduction on both the sides we have problems which are in P, and this transformation should have been done should not be more complex than the problem itself. I mean to say. So
Yeah.
what kind of transformation is this?
Yeah. So here, I mean, in the question we are asking for, we are still asking for NP complete. I mean, whether A is NP complete, even though we now, I mean, even though we are assuming that P and NP are same. So in that sense, NP complete and P complete would be the same notions. But when we defined NP complete, we clearly said that this should be a polytime many one reduction. Okay, so therefore, in the context, I mean, with respect to this question, we are only talking about polytime many one reductions. Okay, but if it so happens that P is equal to NP, then your notion of um, this is, it would be more correct to call it P complete. So now that we are in a smaller class, the notion of reduction should potentially be smaller. So you can then define, so if it so happens that P is equal to NP, then everything is here. Then you, if you want to refine this further, then you can go on looking for finer kinds of reductions like NC0 reductions or um, log space reductions and so on, depending on your choice of, I mean, how coarse you want it to be or how fine you want the classification to be. You can make your own choices. But that is if this collapse happens, and then we are interested in the question of classifying them further. But for this particular question, we are only talking about NP completeness notion, so we will stick to this definition.
Yeah, thanks. And what's the meaning of this diagram you draw here? I mean,
Uh,
what what does it imply?
yeah, that you have if P is equal to NP, then you have all your NP problems here. Now, I mean, they are one and the same classes, right? So if you want to classify them further, then you can say that these are um, these are um, yeah, these are the problems that are, let's say, P complete, in the sense that for all A in P, um, A reduces to B in L, or you can say that A reduces to B in NC0 or something, some notion of your choice, then you'll say that B is here, and you'll try to refine this set further.
So yeah, but then I could not understand because in one of your classes, I forgot you draw a diagram illustrating this fact that if A and B, then the reduction, I mean the transformation should be less complex than the problem itself. And to illustrate this thing, you used to draw a diagram, and this diagram is not one of them. That was something else. Would it be possible for you to draw that diagram showing this thing that the reduction should be less complex than the problem itself? What was that?
Okay, I'm not sure which diagram exactly, but I can just explain this further. So let me, yeah, yeah. So yeah, you are right. So the point is that if A reduces to B, and we are talking about A and B are languages in A and B are languages in P, then of course all languages excluding sigma star and phi, they all reduce to each other in polynomial time many-one reduction. In that case, you'll just have this diagram, right? Everything is here. But if you want to classify the hardness further, you want to look inside this and find harder, like among those set of P languages, you want to somehow find the hardest of those, then you'll look for a notion different from this, right? It will be more refined. So what is one possible notion you have? um, what lies inside P? You know, there is NL, there is L, then there are NC0, NC1, NC0, and so on, right? So the I mean, the lower the class you take, the finer and finer the reduction will be. So if I choose, let's say, if I choose L to be my, or let's say not L, if I choose um, NC1 to be my notion of reduction, so I'm talking about this, then this diagram would be that I'll say that um, within P there lies a class of languages which I shall call P complete, and they are P complete if they are in P in the first place, and secondly all these languages inside P reduce to B under the notion of NC1 or whatever. I mean, okay, I mean, you want this to be smaller, otherwise everything will collapse um, to the same class that you began with.
Yeah, thanks for this. And what did you say at the end? That the reduction should be the smaller one, otherwise everything will get collapsed. What does it mean?
Yeah, if you have, for example, if we don't take NC1, if I take P, then I mean, because A and B itself are in P, you can always, for every language A and B, you can always come up with a reduction like this in polynomial time.
Yes, I understood this one. Yeah, thank you
Yeah.
so much. Yeah, now I understood this. Thanks.
Ma'am, what thing realize polytime many one reduction? Can you give again an example?
What do we mean by polynomial time reductions? Is it,
Polytime, you are pronunciation this terminology. Polytime many one reduction.
yeah, you want me to define that? Uh, that's
Yes,
the
yes,
question,
yes.
huh? So yeah, so we have this reduction, right? So this is what we mean by a reduction, that B reduces to A if for every instance X in B, um, X is in the language B if and only if the transformation sigma of X is in A. So this sigma is our reduction. So we'll say this P here denotes that this is a polynomial time reduction. By that we mean, given X, we can compute sigma of X in polynomial time. Okay. um,
Compute sigma of x means what? Here, what thing represented here?
so sigma is a function from sigma star to sigma star. What it does is, given a string X in B, it will uh, transform it into another string in sigma star, which is what we call sigma of x. It's a function. It's a many one function. Okay.
Ma'am, sigma star, arrow, sigma star, this is the same thing, but why arrow is represented?
These are sets. Okay, so on this side, okay, 1 second, someone is in the call. Just give me a second. Okay, how do I admit from here? Yeah, sorry, I'll have to share the screen once again. Uh, okay, sorry. Okay, so we have this, yeah, you have this function sigma from sigma star to sigma star. So this is the set sigma star, this is the set sigma star, and what it could do is, let's say it looks at a string 0 here, it can map it to a string 1 0. If it looks at 1 here, it can map it to 1 1. So it's mapping some strings here to some strings here. That's why although the sets are same, they are transforming strings. The function is transforming strings from here into some other string.
Okay, ma'am. Understood.
Okay. Okay. Yeah, and many one just means that this function is a many one function, that several strings here can go to the same string in the set, in the other set. Okay. Yeah, any other questions?
Ma'am, polytime means what?
Yeah, so given,
Poly-
yeah, given,
Polynomial time.
right, right, yeah. Okay. Um, yeah, and also I think at some point, Goyal, you had asked about the different notions of reductions.
Yes, yes. Yeah.
Okay.
Carp reduction and then Manitoba reduction and Turing reduction.
Yeah, any idea if the Turing reductions are covered uh, in the course?
So Turing reduction as such has not been covered. But then you told this thing once that so if we are doing reduction multiple times and with the reduced instance,
Hmm.
probably we would be I mean how to say this, but then we would be like say, so if I view a decision problem, so if I look for the search form of the decision variant, so then what would I do? So I keep on calling this decision variant multiple number of the time, and each time I would be reducing
Hmm.
the size of the instances. So that is equivalent of the Turing reduction, I guess.
Mm,
Like
okay,
say
so
decision variant, yeah. Please.
Hmm. Okay. Yeah, so that is one of the differences. So in many one reductions, what you are okay in the reductions that we have been doing so far are many one reductions where the sigma from a to b is this function is a many one function. That's all, and yeah. Okay. So this many one is the notion that we are familiar with. That's what we've been using so far, and yeah, and Turing reduction says that. So this is denoted by capital T. Okay. Hmm. Okay. Yeah. So this is what you meant, right? So you can assume that B is given as an oracle to you, and you can keep on asking queries to B and use those answers to B to get your answer to A. Whereas here, what we are really doing is X is being transformed into sigma of X, and then you are using the answer of sigma X. If sigma X is says yes, I mean by yes, what we mean is sigma X is in B, then you are going to conclude that X is in A, and if sigma X is not in B, then you are going to conclude that X is not in A. So this is sort of like you are using only one query to B. That's all. Like you are just going to transform X into sigma of X and check if that belongs to B. Based on that, you are going to take a decision whether X is in the language or not. Whereas one difference that you mentioned is like you mentioned is that you can think of uh, this as you're allowed to use multiple queries to B. So what A will potentially do is use, let's say input of X is A, then it can keep on querying um, B on whatever input it wants, and you can make this query several times. So how many times, that depends on what sort of a notion of time you are dealing with. If you say polynomial time, then by default the number of queries will be limited by polynomial. So you can make several queries on as many queries as you want, and then you can, based on the answers, you can decide. It could be a complex function of maybe it says yes here, no here, and so on. Based on that, you can take a decision whether to accept or not. Okay, so that is one of the differences. So now you have two different notions, which is a stronger notion. Can you say that if A Turing okay, wait, somebody wants to join the call. Okay, sorry, I'll have to exit and admit the person again. So this is behaving very weirdly today. Okay, so yeah, sorry. Hmm. So one difference, of course, is that here you are allowed to make only one query, whereas here you can think of having an oracle access to B, and you can keep on making several multiple queries to B, and then decide whether to accept or not. So which is a stronger notion? So which is a stronger notion of reduction? So how do we say that one is a stronger notion? If A many 1 reduces to B, then does this imply that A also Turing reduces to B? And second thing would be, if A Turing reduces to B, then can we say that A many 1 reduces to B? Okay.
Second one is correct. Second one is correct.
Yeah. So second one is correct, because if A Turing reduces to B, then what you'll do is, oh sorry, it's the other way around, right? A should be correct, right? If A many 1 reduces to B, then what you'll do is, it makes just one query, right? It makes sigma, it just takes for membership of sigmax. You can do the same thing here, right? You'll just ask the oracle whether sigma of x is in B. So if this is allowed to make multiple queries and you're just using one query, that's still fine, right?
So multiple would mean one. Multiple includes one. So
Correct, correct.
therefore, yeah. So therefore, if A is getting Turing reduced into B, then this implies that this A is also getting many to one reduced to B.
No.
However,
Huh.
yeah.
Okay, go on. Yeah, sorry, complete that. Yeah.
However, its converse would imply that whenever I have many to one reduction to B, then I can query to B multiple number of the times. Then only the A is Turing reducible to B, and that is not the case here. So I'll prefer option two.
Okay. So, um, okay. So let's say that A many 1 reduces to B. Okay. So that means there is some function sigma which is going to query whether sigma of x is in B. And if B says yes, then you'll say yes, otherwise you say no. So why can't I do the same thing here? Here A is allowed to make multiple queries to B, but A doesn't do that. Let's say, I mean, instead of making so many queries, it will just query B on sigma of x. And if so, A queries B on sigma of x, it's allowed to make multiple queries, but it's not necessary that it should make, or it can make but it may not even use those. So maybe it does make several other queries, but it's not even going to look at the answers of those. In the end, it will only look at the first query's answer. If sigma x was in B, then you will say that x is in A, and vice versa. Okay, and if sigma of x was not in B, then you will say that x is not in A. So it is allowed to make multiple queries, but it can also just make one query, or make multiple queries but not even look at their answers.
Makes sense, because if I can get answer in in just by asking one question, that
Hmm.
technique should be more powerful compared to the one wherein I am getting answer after asking multiple questions.
Hmm.
So therefore, the many to one now, I mean, on the basis of this argument, many to one seems powerful compared to the Turing reduction. Or
Mm,
whenever, no, no, not powerful. So what's the meaning of this symbol here implies here? That
this.
whenever there is a many to one reduction, this will always imply the Turing reduction.
Hmm.
That is
Hmm.
fine.
Hmm.
But then whenever there is a Turing reduction, that may not imply the many to one reduction. Oh, in that sense,
Exactly.
yes, the
Yeah.
option number one is correct. Right.
Yeah.
Right.
Yeah.
Yes.
So in fact, so one is correct, but two is not. We can come up with a simple counter example. So intuitive idea would be that, okay, A makes several queries to B. So how can I get the answer in just one query? Okay, that is intuitively why this should not work. But then you can also say that, okay, if A makes so many queries to B, why don't I concatenate them and then pass it as a single query and so on? But it doesn't work because of a simple counter example. So here notice that I'm not specifying any um, notion of time. I did not write a p here or anything. Okay, so I'm not worried about the time right now. So I'll go back to the computability world, where also you can come define the same notion of Turing reduction. Okay, so if for example is the halting problem, okay, and B is the complement of halting problem, okay, then HP Turing reduces to HP complement. So why is that?
Can you repeat this
Yeah,
question?
yeah. I'll get this on the other page. Okay. Okay. So okay. So you have that A Turing reduces to B. Okay. And let's say that HP, okay, basically I'm asking you to prove that HP Turing reduces to HP complement.
So that would mean that when the halting problem, so what would be the complement of the halting problem? That M does not halt on W. So if M halts on W, then how to query this M halts on W, M halts on W. Okay, so I'll keep on asking to this P multiple time that does this M halt on W, and every time I would be expecting a no. So in that sense, because in the case of this, the complement of HP, uh, I think that we are interested in getting the answer of no and not the answer of yes. So yes, we can query to be to the multiple times, and in that sense, the halting problem can be reduced into its complement.
Yeah, in fact, you don't need to query multiple times because what you'll do is input to you is m comma x. This is the input to the halting problem. Now, what you do is you ask the HP complement oracle, right? This is what you have. You're going to ask the HP complement oracle if mx is in HP complement, right? And if the oracle says yes, then what you know is that mx is in HP complement. This implies that mx is not in HP because HP and HP complement are basically complement languages of each other, and therefore what HP will do is HP will say no, m does not halt on x. Similarly, if this oracle were to say that no, uh, mx is not a member of HP complement, that means mx must be in HP complement, which is nothing but HP, and therefore HP would say yes. So basically, what it's doing is that it's asking whether its input is in HP complement or not. And if the answer is yes here, then you will say no. If the answer is no here, then you will say yes, because HP and HP complement are basically, I mean, HP is nothing but sigma star minus, yeah, that's the complementary language that you have. So you just need one query.
Yes, yes.
Yeah, so this part is true, but what about this? What can you say about whether HP many one reduces to HP complement?
So that will not be feasible. That will not be feasible.
Yeah, that cannot happen because otherwise you'll, if HP many one reduces to, yeah, if HP many one reduces to HP complement, what this would mean by definition is that HP complement is SD hard, or um, yeah, I mean, then you will not have this sort of a distinction here. That, I mean, in case of SD and co-SD, there is a uh, clear I mean, mm, bifurcation, right? So otherwise you'll have that they are both SD, which is not the case. So you cannot have such a reduction, is not feasible. So you know that this is not necessarily correct. So not necessarily true. And here is the counter example by, Okay, so yeah, so what we did so far is we defined, so many one reduction is the same notion that we had during reduction. This is that you have an oracle access to B, you can keep on querying to B as many times as you want, and then you come up with a decision whether to accept or not. So um yeah, okay, and this is the comparison between the two, that if A many one reduces to B, it also Turing reduces to B, but the other way around is not necessarily true. Okay, and what about the carb reductions? So carb reductions is exactly same as many one reductions, but we are additionally insisting that the reduction is polynomial time reduction. Okay, so that would mean A many one reduces to B, but also it's a polytime reduction. And this is just A. Okay, these are the notations. Okay.
Ma'am,
Yes.
I want to be justified all non-trivial problem in NP become NP complete. Some please give me some condition.
You want to know if all the languages, if NP complete is same as NP.
All non-trivial problems in NP become NP complete.
Okay, so you're asking when does this happen or what will happen if this happens?
Yes, yes.
What will happen if NP is equal to NP complete? Okay, so okay, but about the reductions and the definitions that we saw, are there any questions before we move to that?
So this reduction part is fine, but then while doing the many to one reduction, and since the exponential time is also allowed, so in that case, what would be the nature of these two problems, say A and B? Are they undecidable, or is this possible that they are not undecidable and still we can go for the uh, but even if, I mean, when to use which reduction? When to use which reduction would be the appropriate question. When to use car, when to use many to one, when to go for Turing.
Okay, so in 2 and 3, that is in many one and during reductions, we did not specify the, sorry, yeah, we did not specify this time here. Okay, so both the notions are valid in computability world as well as in the complexity world. So you can talk about these reductions in when you're talking about semi-decidable languages, or even higher, SD to the SD and so on. Okay, just make sure that both the language, both A and B are in appropriate classes. That is, it shouldn't be that B is a semi-decidable language whereas A is a harder language, that is SD to the SD and so on. As long as we are maintaining the sanity check that either they are in the same class, or one is clearly like this is higher or harder than the other. As long as that is true, both these reductions are valid in the computability world. Now when you um, talk about notion of time, that is where uh, we know that the we know that they are both decidable languages if A and B are decidable, and now we are asking about the complexity, that is the time. So most in most cases we are dealing with polynomial time reductions, and then you come to this notion of CAP. um, but if you are dealing in a class that is inside P, or a much smaller class, then as we said earlier, you'll have to define this notion appropriately. Okay.
Yes, yes. It's clear to
Does
me.
that answer the question?
Yes, yes, thanks. Yeah.
Ma'am, please, if a problem repeatedly happen polynomial time reduction, then what happen do after next?
Mm, as in if A reduces to B reduces to C, and so on.
Yes, any example, any problem. So the possible feasible problem. So I can ask that type of.
Oh, okay. Wait. Let me understand your question first. So, are you saying that if A reduces to B, let's say many one reduces to B, and B many one reduces to C, and C many one reduces to D further. So, are you asking whether what can we say about A and D?
Yes, it is true, but yes, you can posit this. Then I can understood.
Yeah. Okay. So, if you have a series of reductions like this, then this would imply that A many one reduces to C, A many one reduces to D, and so on. All sorts of um, I mean, you can derive all sorts of conclusions from this because this is a transitive relation. Okay. So if basically we just mean if A many one reduces to B and B many one reduces to C, then this implies that A many one reduces to C, because you can look at the underlying function here. Let's say this is sigma 1 and the underlying function in this reduction is sigma 2, then you can come up with a new function which is sigma 1 composed with sigma 2, and you have your reduction from A to C. So if you repeatedly keep on applying this, you'll get all these sorts of um, yeah, conclusions.
Okay, ma'am. Transitive relation will happen.
Yeah,
Actually.
yeah. Okay. Okay, and so okay. And what was the other question? You are asking if NP complete is equal to NP, then what are the consequences?
My question was that all non-trivial poly problems in NP become NP, but I want to just justify it. So non-trivial means language that is neither empty or not universal. So that things.
Okay, so let's say A is a language in NP and A is non-trivial, that is um, A is not equal to phi and A is not equal to sigma star, and if A is in P, then what do we say?
A is an NP complete become.
Yeah, that's what we mean by this, that all languages in NP now become NP complete.
Yes, yes.
Yeah. So yeah, these are the same things. So okay. So yeah. So then and this is your set of NP complete languages, this is your set of P. Okay, then this would in particular uh, yeah, in particular this would imply that okay, sorry, let me just think about it for one. Hmm. Okay, sure. So let's say that there's a language A which is inside P. Okay, so A is a language in P, and therefore by definition A is also in NP. Correct. So now you know that NP is same as NP complete language. So therefore this implies that A is NP complete. Correct. So um, so this is by the assumption that we made in the question. Okay, and yeah, assume that A is not phi and A is not sigma star, because we would need that for the NP completeness definition. As we saw earlier, right, you need that sanity to hold. Therefore, you assume that A is not empty and A is not sigma star. Okay. So now, what this means is that for all B in NP, you have uh, B reduces to A in under polynomial time many one reductions. This is by definition. So that would mean that B is also in P, because what you do is, given this input, given an instance in B, you're going to reduce it to an instance in A. You're going to, so x is in B, we are going to convert this to sigma of x in this can be done in polynomial time because the reduction is in P, and now we are going to check if sigma of x is in A, and this we can check, this check can be, sorry, this check is in P. Why is this in P? Because A itself is in P. This is the assumption we made. A is in P, therefore you can make this check in P, and therefore if A says yes, then you are going to conclude that x is in B, and if A says no, then you're going to conclude that x is not in B. Therefore this entire language B becomes in polynomial time. Okay, so what does that mean? That means P is equal to NP, because every language B which is in NP is now in P. Therefore the two sets must coincide. Does this make sense, or do you want
Yes,
me?
it is necessary to go through this illustration. So I think this is a okay.
Okay, yeah. Um, yeah, is everyone fine with the argument?
Yes, yes.
Okay, so then we concluded that uh,
But we often talk about the quasi NP as well. I mean, which we call NP intermediate, and those language it would be N and NP complete. There is a category of the problems and which are NP intermediate or quasi NP. Yeah. So would it mean that the community believe that every NP is not equals to NP complete, and then there are problems which are there in NP but are not NP complete?
which are not yet known to be NP complete. Yeah, so the general belief is that the two sets, um, NP and NP complete, are different. That is, there are languages here but not, sorry, languages here which are not here, and but that's the belief. I mean, otherwise it would, if this were true, then this would imply that P is equal to NP, and we don't believe that to be true either. So yeah, so this is also something that is maybe unlikely to be.
Yes, fine.
So yeah, what we ended up proving is that then p is equal to n. I'll just remove this. Okay. Okay. So I'll move on to the next question. Yeah. Okay. So what is the satisfiability problem? We defined SAT to be the set of all formulas such that phi has a satisfying assignment, and okay, and when I say phi, you can think of, let's just think of phi as a formula where you have n variables x1 to xn. These are the variables, and what are the clauses? The clauses are conjunction of the variables or their negation. So this is a clause, so you pick some variables or their negations and do a conjunction of them. Sorry, uh, I mean to say you do an or of them. Okay, these are the clauses, and let's say that this is clause C1 for me. The clause C2 could look like x4 or x6 or x1 bar. Okay, I have such m many clauses, and um, what I'm going to do is phi for me would be C1 and C2 and so on up to Cm. So this would look like x1 or x2 bar or x3 and x4 or x6 bar, sorry, or x1 bar and so on. You do a conjunction of all of them. Okay, and when do you say that phi is satisfiable? If there is a 0 1 assignment, so let's say a is a string in 0 1 to the n, and when I say 0 1 to the n, if the string is 0 1 1 0, that means x1 is 0, x2 is 1, x3 is 1 and x4 is 0. That's it. So it's just an assignment to all the variables in that order, x1 to xn. So if you substitute this string here and phi of a evaluates to 1, then phi is satisfiable. Okay, so if there is some 0 1 substitution that we can make to the variables such that this formula evaluates to 1, then you will see that phi is satisfiable and a is a satisfying assignment. Okay, so we know that this problem is NP hard. This is NP complete problem, and here is a modification to the problem. So double sat is the following problem. Phi is a formula that's given to you, and in general it need not be that you have three variables here or three literals here. You can have as many, but normally we look at the three sat instances. So so I'm just writing clauses with three terms, but it does not matter. Okay, so you know that the sat problem is NP complete. You want to show that double sat is NP complete. So what is double sat? Double sat is given phi, check if it has at least two satisfying assignment, and there should be two distinct satisfying assignments. So in other words, so you want to show that double sat, which is the following problem, phi such that phi has at least two satisfying assignment, two distinct satisfying assignments. Okay, and you want to show that double sat is NP complete. Okay, so when you say it is NP complete, you are going to show that it's in NP and you're going to show that it's NP hard. So how do you show that this is in NP? I mean, we have seen like several examples at this point, so we'll not delve into it, but yeah, just quickly, can you tell me how?
So yes, so basically the certificate would be the what should I say, conjunction or the disjunction. So that would be the conjunction of the two satisfying assignments, and that would be of the polynomial length, obviously, and each one of them should satisfy the satisfiability, and both the assignment should be different, and then the problem becomes polytime verifiable.
Yeah, so the certificate would be you'll give A1, A2, where both of them are in zero instance,
Yes, yes. Now
and
the yeah, now the real problem is to show that this is empty hard. So how to transform an instance of the satisfiability into an instance of the double satisfiability? So for that thing, if the satisfiability says no, then this double set says no, that is not the issue. But when the satisfiability says yes, then I'll have to look for one more assignment. And so basically, so how to, when the satisfiability says yes, uh, so what modification should I make in an instance of the satisfiability, so that if I take the negation of the satisfiability, that will become altogether a different problem. That will become tautology kind of thing, I guess. And but since the problem is decision kind of the problem, so satisfiability will only say yes, will not give me the actual assignment of the Boolean literals. Otherwise, I would have included the negation of those assignment of the Boolean literal second time into this instance of the double set, so that I get one more different assignment of the literals. So it is difficult to transform an instance of the set into an instance of double set. I'm able to think now.
yeah. So yeah, you're on the correct line. So I'll just write down whatever you said just now. So naturally, the attempt one would be, let's say that phi is the formula that's given to you, and you just transform like it as it is, and ask double sat whether um, yeah, you're going to ask whether phi has at least two um, satisfying assignments. Phi has at least two satisfying assignments, and if the answer is yes, if the answer is yes, then that means that definitely phi is satisfiable. So in this case, you can safely say that you can safely a can sat yeah, yes, phi is in sat. This is something you can safely conclude. This part is fine, but when it says no, that means it could be that either phi has no satisfying assignments, in which case you know that phi is not in sat. This is fine, but or it could also be that phi has exactly one satisfying assignment. In this case, phi is in sat. Okay, so just based on the answer of whether double sat said yes or no, you can't conclude anything. If it says yes, then yes, sure, you know that it is satisfiable. But if it's no, then you can't distinguish why was it a no. Was it no because phi is not satisfiable, or was it no because phi is satisfiable but there's only one satisfying assignment? So this is the issue that we run into. So this part is the issue. Yeah. So like you said, you would therefore not want to uh, pass this phi as it is. You would want to do some sort of a surgery, transform this into some phi prime, so that now when double sat says no, you want to be conclusively sure that phi is not satisfiable. So yeah. Hmm. Okay, and is I don't know if you meant to say this, but was this what you were trying to do? That you take phi and you um, take a phi double prime where you are just replacing phi double prime is phi with yi's instead of xi's. Basically, you are replicating the same formula, but instead of using the same variables x1 to xn, you are using the variables y1 to yn.
I did not mean to say this
Okay.
kind of a transformation, but so that was not my intent. Yeah, I was trying to say something else.
Okay.
How will this help, by the way?
Yeah, this won't help because if there is a satisfying assignment, if there is exactly one satisfying assignment here, then there will be exactly one satisfying assignment for phi double prime, and therefore altogether you'll just have one satisfying assignment for phi prime.
Yes, yes.
So yeah, this won't work. Um, yeah, so this does not work. Okay, so then what can
Ma'am,
be?
sat- what does satisfied assignment indicates?
That if you substitute um, these x1 to xn's with the specific 0 1 uh, value, some substitution with 0 1 values, then the formula will evaluate to 1.
Okay, okay.
So what we can do when the double set says no, so we can take the negation of the phi. We take the negation of phi, and so what would it mean? That when the double set says no, and I take the complement of phi.
Hmm.
So if I take the complement of phi, what would it mean?
Yeah, but notice that you are only allowed to make one query, right? So you are upfront, you are going to produce a formula and then ask the double sat. I mean, you're just going to make one query, you're not going to repeatedly um, query. Like, you can't do based on the answer, you are going to query it one more time.
Right, right, yes.
So, okay, I had this one idea in mind, but there may be, okay, let's go through it. So, you have this formula phi, and so what if I introduce new variable, and let's say these are y1, y2, y3. I guess you'll probably not even need all of these, but let's say I do this. I do y1 and sorry, this is or, right? So this is my new clause, y1 or y2 or y3. Okay, so observe that if phi is not satisfiable, okay, then no matter what you put here, whether this clause is satisfied or not, if this itself is not satisfiable, then you can never get a 1 because this part is always a 0. So whatever you AND it with, phi prime will also be 0. Then phi prime is not satisfiable. This is what we wanted. This is what we were anyway getting. So this part was, oh, this part is what we solved.
Yes, and I mean, including y1, y2, and y3. So, how will this? How will they? How will they tell that if the this Boolean expression phi is going to have exact one solution? So, after getting a no from the double set, uh,
Yeah. So the other condition, right? If phi is satisfiable, then you want phi prime to have at least two assignments.
yes,
Yeah. So if phi is satisfiable, let's say that suppose A is the assignment, suppose phi of A is equal to 1 for some A in 0, 1 to the n. Then observe that x1 to xn substituted with A and y1, y2, y3 substituted with a 1, 0, 0. This is a satisfying assignment. So this, I'll call this A prime. A prime is as follows. For x1 to xn, you use the same satisfying assignment A. For y1, y2, y3, you substitute as follows. And observe that phi of A prime is equal to 1 because y1 or y2 or y3 is 1 because of this assignment, and A is the satisfying assignment for phi. So therefore A prime is a satisfying assignment. What you could also do is consider A double prime where x1 to xn are the same, substitute them with A, but now you do 0, 1, 0, and now you get phi of A double prime is 1. In fact, you can produce 7 different assignments out of this.
yeah. So my point here is that why don't we instrument this Boolean formula phi in such a way so that this formula along with this phi I include something and which is always true in the sense that yeah, always true kind of the thing. So then for the yes instance, if the Boolean formula phi is satisfiable, then the double set will say yes. Why so? Because now the Boolean formula is having the original formula phi along with something which is always true.
Yeah.
Now regarding the no instance, when the double set says no, so then in that case, clearly that would refer to the case wherein phi is not satisfiable.
Yeah. So the no instance is not an issue. The problem with always with substituting substituting something here which is just always satisfiable. So for example, if you just do um, if you just do phi bar is phi and um, x1 and x1 bar, sorry, x1 or x1 bar, something trivial, this is always true. Okay, the problem with this is that suppose phi is satisfiable. So okay, so suppose you do this, this this part is trivially always true. Doesn't matter, I mean, whether I take y1 or x1, doesn't matter for now. So observe that if phi is satisfiable, okay, then um, and let's say um, A is the assignment which makes phi evaluate to 1, and for all a prime not equal to a, you have that phi of a prime is equal to 0. So there is exactly one satisfying assignment, and that is a. Then what happens to phi prime? How many satisfiable assignments does phi have? Sorry, does phi prime have?
So would be having two, I mean exact two, one assignment and which is already always satisfiable. So this is one assignment, one valid assignment. The other would be corresponding to the literals of the Boolean formula phi. So instead of x1 or x2, you can use some other dummy variables like say y1 or the complement of y1.
Yeah, so what I'm saying is if this is x1 x2 which is actually in phi, then
So instead of taking x1 and x2, better we take say y1 and the
yeah,
y1 and the
if
complement of y1.
yeah, if this is y1 or y2, then there's no, yeah, then there is no issue, because y1 equals 1 will give you one satisfying assignment, y1 equals 0 will give you another satisfying assignment.
Yes.
But
Yes.
the claim that you can just substitute something which is trivially always true is not correct, because here is a counter example. If you
So, but then I meant to say that yes. So I mean anything which is whose literals are different from the literals of phi, but then that always results into something which is satisfiable. So therefore, the yes instance is getting satisfied here. Double set says yes, means the set will also say yes, isn't it?
mm, okay, but you want the following, you want the other guarantee that if phi is satisfiable, then phi prime must have two satisfying assignments. What you said is the converse.
So, like in this case, when phi is having the satisfiable assignment, phi prime would be having two satisfying. Uh, oh, I see. Yes, that's right. I got my mistake.
Hmm. Yeah, but if you take y1 y1 bar here, that will work. But yeah, you have to be, basically whatever you are adding should have at least two satisfying assignments.
Right, right. Yes.
So yeah, so this will only work if you additionally ensure that the added formula has at least, or maybe the condition is just that the added formula has at least two satisfying assignments, and it would be easier to introduce new variables. Then you don't even have to worry about the simultaneous uh, yeah um, values. So okay, yeah, so just to finish the writing part of this, then you have demonstrated that phi prime has at least two satisfying assignments, which are a prime and a double prime. Therefore um, phi prime of the, okay, what do I want to say, yeah, therefore phi prime is in double set. Okay, this is the complete proof. And yeah, the good thing about this reduction is that if I give you um, if I modify this language instead of double sat, if I give you any number, if I give you any number k which is a natural number, then now you know how to use the same proof to come up with um, a reduction for this modified language. So how will you modify the language. So what I'm saying is, instead of 2 here, you want at least k distinct satisfying assignment, and this language you want to show is NP hard.
So then I would be using k plus one number of the whiles.
Yeah, I think log k should work. Log k plus 1, because if you use three new variables, you are able to produce 7 assignments, right?
Yes.
So yeah, but k plus 1 would definitely work. Yeah.
Yeah.
Yeah, good. um, yeah, and although we are not saying it over and over again, but this reduction is a many one polynomial time reduction. It's a carb reduction. Okay. Yeah, which is something that you would have to write in the exam. If it's a descriptive question or whatever, you'll have to mention the type of reduction, the time, etc.
Yes. Yes.
Okay. And yeah, so I mean to say, passing through all vertices exactly once without repetition. Okay.
So, like in this case, checking if a cycle exists in a graph is NP complete. So, is this a cycle of the vertices?
Yeah, yeah.
Okay, all right. So that is the Hamiltonian circuitry, and then Hamiltonian circuitry is NP complete, wherein no, checking if a cycle exists in a graph. No, no. Yeah. So nothing to do with the Hamiltonian circuitry. Checking if a cycle exists in a graph is NP complete, so that I can conduct a DFS to see that whether there is a cycle or not, and DFS is polytime. So therefore, this is incorrect. And checking if a cycle passes through all the vertices in a graph is NP complete without repetition is Hamiltonian circuitry, and this problem is NP complete. And checking if there is a subgraph of the size m and which is isomorphic to km. So showing the graph isomorphism is I don't know. This is NP intermediate kind of thing, and so probably this problem is not NP complete, and this I'm not sure about this. Given a graph G and two vertices S and T, checking if there is a path from S to T is NP complete. So graph connectivity problem is simple. I can use Dijkstra here, and then yeah, so that can solve the problem in the polynomial time. So therefore, one is false, and then two is true, and four is false. And I'm doubtful about the C, but I believe that this is also false. Only B is true.
Okay. Yeah.
I
So let's.
think
Yeah.
both option 2 and option 3 is correct, because option 2 is correct because this is a the Hamiltonian cycle problem, and because visit every vertex exactly once and return, and classic NP complete problem. And number 2 is number 3 option number 3, this is click problem. Find k vertices all connected to each other. So one of the most famous NP complete problem.
Yeah. Yeah. That's correct. So yeah. So A is nothing but um, checking whether the graph has a cycle. So you can just do your BFS DFS algorithm, and this problem is in P. Okay. And similarly, yeah, the problem D is nothing but ST path problem. Okay. And again, you can do a BFS etc. and check whether there is a path or not. So this is also in P. This is, yeah, you can do. So these two statements are in P, but we don't know whether they are NP complete. If we knew that they are NP complete, then we would have P equals NP, which is something we don't know. So these two statements are not known to be true. Um, okay, and whereas B and C are true. So, okay, so as you observed correctly, B is the Hamiltonian cycle, yeah, Hamiltonian cycle problem, where you want to, given a graph G, check if there is a cycle which passes through all vertices exactly once, and this is something that is known to be NP complete. So this is fine. And for the C part, we are asking whether um, yeah, given a graph G, oh, okay, okay, yeah, so I think that is one, I mean, whatever you said about the click problem, that is correct, but I think there's one subtle detail here. So, okay, the problem that's given to you is that given a graph G, check if G contains okay, okay, check if G contains check if there is a H inside G such that yeah, size of H is K, that is, it is on, sorry, M number of vertices, and H is isomorphic to Km. That is, we are basically, this is same as asking um, equivalently, given G and M as input, check if G has a click of size M, because that basically means that there is a subgraph H which is isomorphic to the click on M vertices, and H is inside G. So this problem is nothing but the click problem, and you know that click is NP complete. So C is correct, and um yeah, the only yeah, I mean, I'm just modifying the problem slightly. So let's say that furthermore, you know that um, G itself is a graph on M vertices. If that's something that you know, then the problem becomes easy, right?
I could not understand this. So what is the modification?
Yeah, so um, G itself is a graph on M vertices. That's something um that you are given. I mean,
Oh yes, it is sufficient to show that whether all the M vertices are connected to one another or not,
yeah,
and that can be done in an effort of the order of M square.
yeah, yeah. In fact, if you are given an adjacency matrix, then you just go through the entire matrix and check if there is a zero. If there's a zero, then uh, I mean, in the non-diagonal entries, then you say that yeah, there's no click of size.
Yes, yes, right.
Yeah. Yeah, so for a minute I actually got confused whether we know that G has M vertices or not, but yeah, that's not something that's mentioned in the question. So B is, sorry, C is an NP complete.
Yes, yes.
So, okay. Hmm. Okay. So here is another problem that you would have probably heard of. This is the traveling salesman problem. And okay, maybe I'll not. And what is the problem? You are given as input a graph G. So there are several cities, and assume that it's a complete graph. Okay, that is from city A to city B there is a path. So from every city you have connectivity to every other city. It's a complete graph, although I'm not drawing all the edges, but it's a complete graph. And what you want to do is you want to start at one vertex, you want to cover all of them, okay, but you don't want to repeat. uh, okay, and every time you travel, let's say you travel from A to B, there is some cost that you are paying. Maybe it's the cost of fuel that you need to reach from A to B, so there is some weight associated with it. So let's say the weight of this edge is W1, the weight of this edge is W2, and so on. Every age has a weight associated with it. So if you travel from A to B to C to D, then you are paying this total cost of W1 plus W2 to W1 plus W2 plus W3. What you want to do is you want to find a Hamiltonian cycle here. You want to go from um, you want to go through all the cities exactly once, and you want to reach back where you started. So it's a Hamiltonian cycle, but among all possible Hamiltonian cycles, you want to output the one whose cost is minimum. So find a minimum cost Hamiltonian cycle, because if there are several possible ways to complete this tour, you would want to minimize on the cost that you ended up paying. Okay, so the decision version of this problem would be that given a graph G and a number K, or let's say C, which is the cost. Okay, let me say Z. Okay, check if G has a Ham cycle or tour, Hamiltonian tour of cost, total cost C. Okay, so okay, and also notice that the graph is complete. So between any 2 points there is an edge. Okay, so what you want to do is you want to show that this problem TSP is NP complete. So how would you attempt to do that?
So obviously we would be reducing the Hem cycle into the TSP, but then the Hem cycle needs to be applied in a slightly different way, probably by modifying uh, the weights here. Uh, yeah.
Yeah, so so that is a correct observation. You would take your Hamiltonian cycle problem and you will reduce it to the TSP instance. So you are given a graph G, you want to come up with a graph G prime and a cost C. So the reason I'm writing G prime here is that it can't be G itself, because well, one reason is that G prime is a weighted graph, but the other reason is also that G prime must be a complete graph, whereas G need not be. So G prime must be a complete graph. I mean, I guess that's how we defined it here, right? Okay, let us assume. Yeah, let us assume it for now that it's a complete graph.
Complete or connected?
Yeah, it must be connected, otherwise you can't even come with a tool, right? Um, I mean, G itself must be connected, otherwise you'll, I mean, otherwise the instance becomes easy, right? If G is not connected, and you know that there's no TSP, there's no Hamiltonian cycle.
Yes. So if we assume the weight of the every edge is equal to 1, and if there exists a Hamiltonian path, then the sum of the weights assigned to the edges definitely would be equals to what? Would be equals to the, because this is Hamiltonian, so depending upon the number of the vertices, like if there are k number of the vertices or p number of the vertices, then the length of the path would be equals to at least p. And but so how to include this weight factor into an instance of the Hamiltonian cycle?
Hmm.
So if I consider the weight of every edge as the unit weight, so how will it help me? And
Yeah. So let's just we take one example. So
First of all, it we should prove a TSP belongs to NP, and next step is to prove TSP belong to NP hard. Now, a question is how will I prove NP TSP belongs to NP? So, to a certificate or a sequence of vertices, we can verify it to visit all vertices once. So it forms a cycle. Total cost less than equal to k. So it verification takes the polynomial time. So therefore TSP is NP belongs to NP. Next is TSP is NP hard. We reduce from a Hamiltonian cycle problem, which is NP complete. So construct a complete graph and with same vertices and assign the weight and set k equal to v. So that's way we can prove this, which is a TSP is NP complete.
yeah. So in the weight assignment function, what you're doing is so G is not um, a complete graph by itself, right? G need not be complete, but you want this G prime to be complete. So what I mean to say, if this is your G, let's just say 1, 2, 3, okay, so A, B, C, D, E, F. Okay, and what you're saying is that I'm going to modify, yeah, yeah. I'm going to modify this by saying that okay, now here the weight function is going to be that, let's say all these edges have a weight of 1. Okay, so the weight part is taken care of, but I additionally insist that this new graph must be a complete graph. So there will be these edges. There will be all these edges, right, which were not there earlier, but they are there now. So yeah, I might have missed one or two edges, but yeah, assume that it's a complete graph. And now because it's a weighted graph, you said that the original edges must get a weight of 1. The blue edges, which are the original edges, get a weight of 1. But what do I sorry but what do I do with the red edges? What weight should be given to them, so that um, let's say n is the number of vertices here, okay, so that there is a TSP of cost n whenever um, the original graph had a Hamiltonian cycle. If there was no Hamiltonian cycle here, then you don't want a TSP of length n. So basically you want some weight function on the red edges as well.
Right. And uh,
And it definitely can't be 1. If you give it a weight of 1, then there's no way to distinguish whether it was an original age or it was the added age. So the only question is whether they should be larger than 1 or they should be smaller than 1. So should those be 2 or should those be 0?
right. So to distinguish them from the original ages,
Hmm.
we assign some other weights to these additional ages. And these ages could be what? Does it have anything to do with the value k and which was given in the question?
Hmm.
And so, since I mean, really root one everywhere, so these ages should become the uh, part of the solution. Like so, so if I've been given n number of the vertices, then this weight should be equals to k minus n, k minus n. Uh,
K minus n, but
and like so because for the remaining other say if I take all the if I consider all the n vertices, then the sum of the weights would be equals to n of the original ages. And without going through these additional ages, I cannot get the Hamiltonian cycle.
right.
So so in that sense, this n minus k is not the right answer, but yeah,
Yeah. So yeah, if let's say this was your original um, graph ABCD, and what the new graph looks like is you're going to assign a weight of 1, and notice that there is no Hamiltonian path here. Sorry, no Hamiltonian cycle here. But if I give a weight lesser than 1, let's say these edges don't cost me anything, then what would happen is in the new graph you get a tour, but also the cost is matching. So there is a tour of cost C, which is 3 because n was okay, sorry, n was 4 for us. Hmm. Okay, I guess this would also work for us. Oh, okay. Um, hmm. Okay, so n is 4 and c is 4, but there does not exist. There's a Yeah, there is a tour of cos 3, but um, okay. So depends on, sorry, just to clarify the confusion. So um, when you say a cost C here, you I mean, the question is whether you mean exactly C or do you mean at most C? Okay, so normally, yeah, normally when we define this problem, so let's say the vertex cover problem, you are given a graph G and a number K, you are asking whether there's a vertex cover of size at most K. Um, right. So in that sense, the natural decision version here would be: is there a cycle of a Hamiltonian tour of cost at most C? But if you define this to be exactly C, if that is the decision version that you are working with, then this would work. That all the other edges get a weight of 0. So you will never um, yeah, you'll never end up with this um, with a tour of cost equal to 4. Okay, so yeah,
yes, zero is fine. Zero is
the
fine.
0 is fine if we are dealing with equality, but if in case we meant at most here, then the 0 doesn't work, then you'll have to work with 2, if we are working with the definition of at most. So then what you do is, you make all the other edges of weight of weight 2, so that now whichever tour you take, you are definitely using a red edge, because the just by taking blue ones, any combination of them does not work. So if there is a tour, if there is um a Hamiltonian tour, then it must take at least one red edge, in which case the cost of this Hamiltonian tour would be greater than n, because you are choosing something. So this n is something you get only if you take all the blue edges, because each edge is going to cost you 1. So if you take n edges, you will end up making a cost of n. But if you end up taking a red edge, you are definitely increasing that cost, so you'll go beyond this budget of n. So it's just a matter of convention. If you are defining this to be at most, then make the new edges of cost greater than 1, so that this exceeds. Otherwise, if it's the definition of equality, then this would also go.
Yes, yes. And because of this modification, because we just need to assign the weights to the red edges appropriately depending upon
Hmm.
the limit, the threshold given in the question.
Hmm.
So, but then since this, I mean, adding these red edges, etc., I mean, does not require much extra effort. So, since Hamiltonian hem cycle is NP hard, so therefore the TSP is.
Yeah. So yeah, so this was the reduction part. And yeah, as Saurabh mentioned, the membership in NP is something that can be um, done. I mean, we have seen several examples at this point. Yeah, so yeah, are there any questions about the topics related to today, or any questions that we saw today?
But then this TSP is much investigated problem because maybe because of its business relevance.
Correct.
So in the, I mean, in the landscape of the NP complete problems, compared to the TSP, I mean, what is the situation of the problems which we usually encounter? Like, say, for the satisfiability problems, we do have the set solvers available online. But then probably, and then for the like the TSP things, probably we have some better solutions for this. So what is the situation of the popular NP complete problems?
Okay, so yeah, so as you mentioned, there are SAT solvers already. In fact, for a lot of NP complete problems, there are now solvers that work good enough. Okay, but among these problems, there are I would still say that in the landscape, the TSP problem um, is kind of harder, because it's even hard to approximate. Okay, so the TSP is sort of notoriously hard in that sense. So because if I want to check whether okay, maybe don't tell me that whether fee is satisfiable or not, I'll make a compromise. The compromise is that tell me if um, at least, so this happens, fee is satisfiable when all clauses, let's say there are m clauses, all m clauses are satisfiable, because phi was c1 and c2 and cm. Okay, what I'm saying is, okay, maybe you are not able to um, check if all of them are satisfiable. Instead, what you do is tell me if at least, let's say, um, 3/5 of them, or some ratio. Okay, check if at least 3/5 of the clauses are satisfiable. So this is some kind of a relaxation that we are putting here, right? In terms of yeah, in terms of the other problems, maybe okay. So the notion of approximation would make sense when we are talking about the quantity, right? So in case of TSP, what that means is maybe you don't tell me the optimum cost C, but I mean that was the question. You want to find the optimum cost, the minimum cost tour among all of these. Therefore, we had this decision problem formulated. So you are interested in the minimum cost C, but let's say that is hard to find. Maybe the minimum thing is hard to find, but can you approximate it? Maybe don't tell me the minimum, but just give me a guarantee that whatever solution you are giving, it is at most twice or thrice as bad as the minimum cost. So that is the kind of approximations we are dealing with. So approximations would be, um, you want minimum sized vertex cover. Maybe I'll be okay with if you give me two times the minimum sized vertex cover, this sort of a guarantee. So in terms of TSP, that would be, maybe don't give me the optimum cost C, but let's say C is the optimum cost or the minimum cost TSP. But is there an algorithm that gives me some maybe epsilon, or okay, some constant k times the minimum TSP, which was C for us. So these sorts of algorithms are known in case of vertex cover, in case of independent set, and so on. For a lot of problems, we in fact we know much better than two. So these sorts of approximations are known. There are polynomial time algorithms which will give these, but even approximating TSP, so even if let's say I allow K to be very large, even approximating this is hard, is an NP hard problem. So checking if given graph G, um, there is there a TSP, is there a Hamiltonian cycle with cost at most some constant k times the minimum cost. Even checking this is an NP hard problem. Okay, so in that sense, yeah, in that sense, this is a harder problem. And if you, I mean, approximation is just one way of dealing with it. Then you can ask about randomized and so on. So certain problems become easily solvable when you allow randomization, but some of them remain hard. So um, yeah, in terms of complexity, if we want to compare the hardness, this is what we know. But in terms of solvers, there are now very good solvers for, I mean, almost, I guess, yeah, any NP complete problem that you want.
Yes, yes, yeah, thanks. And while analyzing these problems, I mean, people also look for the parameterization or some kind of the fixed point tractability kind of the thing. So, I mean, how to know that for which problem, which technique works better? Like for which problem the approximation may work, for this problem we can go for the parameterization, or I mean, how to look for the characteristics of the NP complete problem so as to tackle it? How to cope up with those problems which have been proved as NP complete? So what is that? So what that recipe is?
Okay, so yeah, upfront, I mean, these sorts of reduction techniques will not, um, I mean, will not work at all, right? Because all these problems are, so I mean, even though we know that vertex cover reduces to independent set, we can't say that a two approximation for vertex cover will give a two approximation for independent set, or a parameterized algorithm for vertex cover will also uh, transfer into an independent set problem. In fact, I mean, now that you mention about parameterized, we do know that vertex cover is sort of easy for you. You have many good FPTs for vertex cover, but independent set is a hard problem in terms of parameterization. They have this W1 hardness, etc., right? So although they look very similar, one, I mean, we saw that there was a very simple reduction from vertex cover to independent set, but even though it's a very simple reduction, one problem becomes easy for FPTs and the other problem becomes hard. So yeah, understanding what makes a problem hard, that is, um, I mean, that would be a new study altogether. I don't think we do know at the moment why, for example, TSP becomes hard for approximation while others are not, and so on. So I mean, yeah, if you put certain restrictions, understanding which problems will become hard, that's a nice question to ask, but I think we do not know at the moment. So the best thing that, I mean that one does is use intuition and try to find FPT. If that does not work out, then try to find approximations and so on. So um, yeah, I mean, it's more of a trial um, sort of quest. That's what I think.
Yeah, thank you so much. Thanks.
Ma'am, escaped traveling salesman problem.
Sorry.
It's escaped traveling salesman problem and Hamiltonian path cycle. So another others problem have in real life NPR problem.
Okay. Um, okay, so all these games that, I mean, if you care about all these games that we saw, right? One player games such as such as Sudoku or any kind of one player games that you can imagine, those are NP hard, like we saw. If you um, if you give a solution, it's easy to verify, but it's yeah, I mean, yeah, you there are reductions which are non-trivial. So um, okay, so I mean, that would be one, checking if a given game has a winning strategy, or um, yeah, I'm there is this problem called Steiner tree problem, which is also NP hard. um, yeah, this is also NP complete. um, and this is very relevant because it has applications to the circuit design. So um, so if you want to design a circuit, you would want, like, you have these wires and gates and everything, and you want to use as minimum wires as possible in order to implement that circuit, because that would mean your circuit has smaller space, it heats up lesser, and so on. So naturally you want to use as minimum wires as possible. And the Steiner tree problem captures this constraint. So I don't remember the exact problem, but you are given a tree, um, yeah, and the edges have cost. So yeah, and I don't remember what is it exactly that you want to minimize, but yeah, I mean, it has some connection to the circuit design.
So this standard tree is a variation of the minimum aspiring tree, wherein we need to find in the MST we need to find the minimum set. I mean, what the in the MST we have to find the subset of the edges a cyclic subset of the edges connecting all the vertices such that the sum of the cost assigned to the edges is minimum. So, but that was a cyclic subset of the edges connecting all the vertices. And now, in the case of the standard tree, this is the acyclic subset of the edges connecting some of the definitely connecting some of the vertices, not all the vertices, a subset
I
of the
see. Okay, so
vertices.
the input G is not necessarily a tree.
Input is the graph only. Input is the undirected graph only,
Okay.
and
Hmm.
similar to the MST.
Hmm.
The
I
difference
see.
in between
Okay.
the MST and the standard tree is that in the
Yeah.
MST
You
we have to
want
cover all the
all the
vertices,
vertices, right?
and whereas in the standard tree, a subset of the vertices should be covered, and that makes the problem hard.
And you're given a subset S of vertices, and
Yes.
yeah, you want to
Minimize the
minimum cost.
cost
Uh,
of the edges. Yeah, sum of the cost, sum of the widths of the edges, and
on S.
that's
Hmm. So the
being the
minimum
development.
cost
This
will
was
be sum of edges in the tree.
yes. This is an example wherein the covering all the vertices is easy compared to the covering the subset of the vertices.
Yeah. Yeah, kind of similar to this question we saw earlier. If the graph was, if you're not looking for a subgraph which is isomorphic to click, but you're just checking if the graph itself is isomorphic to click, the problem becomes easy. But the moment you want to find a subset which is isomorphic to it, you have so many options to look for now. There are
Yes,
exponential, yeah.
exactly. Yeah. Thanks. Yeah.
Yeah, so these are just a couple of examples that come to my mind right now. But yeah, I mean, there are plenty of problems um, within the set NP. I mean, they are abundant, and a lot of them have real life applications. But yeah, these are just a few of them. You can yeah, I mean, you can look it up. You'll find a lot of literature if you're interested in the real life application.
Okay, I find to that. Thank you.
Yeah. Okay, yeah. So next we will meet on the upcoming Monday, which is same time, 7 p.m. to 9 p.m., and that would be the final lecture. I mean, final tutorial for uh, this course. Yeah.
Which topic shall be covered in this?
I'm not sure what was covered. I probably think maybe space was covered in the lectures. I'm not sure. But yeah, is there anything specific that you want to be covered?
So if you can cover the proof of the Savage theorem,
Proof of uh,
the Savage theorem,
Savage's theorem. Okay. Okay.
and along with some insight over the proof of the Cook-Levin theorem as well.
Okay. So yeah, let's. I'll try to cover it. Yeah, sure. And yeah, there's no extra 13th. I mean, there's no extra problem solving after the next week. So maybe yeah, I'll try to cover up this.
Sure. Thank you so very much. Thanks. Bye.
Yeah. Thank you. Bye.